So our last speaker I met at the Flower AI Summit about maybe it's 6 weeks ago now. I lost track of time, but it's like time moves along. But it's the first time I met Alessio, and actually came with a group of folks from the University of Messina, and they were wonderful people, clearly very knowledgeable about the field, and we had some great interactions at that event. Um, but then he was telling me about some of the work he's been doing. They had some great posters at the event too to show people some of this work. And then we basically wanted to hear more because it was too good to just leave as a poster. So we invited Alessio back to tell us this time at least about because he has a few different sort of projects from the same group. But this time we wanted to hear about the work he's been doing in the direction of homomorphic encryption and how he's been using this with Flower to kind of build really quite secure and privacy preserving types of federated learning. So thank you for joining us today. It's great to have you back. Over to you. We're fascinated to hear what you have been doing.
Okay, thank you very much. Thank you for the invitation. I'm very honored to be virtually here to show a little bit of our work. And so, okay, so let's start. I share my screen now. I'm just one moment. Okay, so could you see my screen, right? So thank you again for this invitation. It was an honor for me to present in this Flower monthly event. It was a very profuse experience at the Flower AI Summit. So we are very happy to show our work and so also in the future about the other poster. So thank you very much. Okay, so let's start with the presentation. So could you see my screen, right? Can you see my screen, right?
Yes. Yes, we can hear. Sorry, I was on mute. Yes.
Perfect. Perfect. So I'm Alessio Catalfamo. I am postdoc at University of Messina. So one of my research interests is in federated learning and in particular also in secure federated learning problem. So we exploit Flower framework to do our research work, and so it's happy for me to be here. So let's start. Let's start with the outline of this presentation. We start talking about the secure federated learning problem, and in particular the secure aggregation solutions. So we talk about homomorphic encryption as solution of secure aggregation. We talk about homomorphic encryption from a practical perspective, and so we also see how we are implemented the homomorphic encryption in Flower in we can say in a standard way, because we would like to provide this solution, this general solution for the community in general. So we'll see some tests, some performance evaluation about our practical implementation, and finally we'll see our future works about this direction. So, as we all know, federated learning is born to train a machine learning model without sharing raw data with a central server. So in federated learning, we have n local data spread among n clients. Each client train a local model, so train local weights and share these weights with a central server. These weights are aggregated in a central server according to a specific strategy. For example, federated averaging, as we all know, is the first strategy introduced in federated learning, in which we have a subset of clients that perform a train task and share their weights to a central server. So as we said also today in the previous presentation, it's not completely secure share local weights or local gradients with a parameter server, because some work in scientific literature proves that starting from weights or starting from gradients, it's possible to reconstruct original data. In particular, if we consider an attacker a man-in-the-middle attacker or a malicious parameter server, he has the possibility to reconstruct original data from weights, from locally trained weights, or from gradients. So in the first case, for example, we can consider the data leakage from gradients. So in this case, it's possible in federated SGD algorithm, where each client doesn't update the local weight, but it share only the gradients. So it perform only the gradients, it compute only the gradients, and it share only the gradients. So starting from gradients, it's possible to reconstruct original data. In particular, if the attacker randomly initialize a dummy sample X and Y, and so we feed this dummy sample into the architecture, into the model architecture. It gets dummy gradients. It can optimize the distance between the dummy gradients with the original gradients. So optimizing this distance with a specific loss function, with a new loss function that is different from the original loss function of client, it can reconstruct the original sample. So with a optimization, it's a optimization problem in which the distance is minimized and the sample data can be leaked. The second case is in the actual federated learning scenario. So the attacker or the malicious aggregator server gets the weights, the locally trained weights. Starting from them, some work in scientific literature design this loss function, this specific loss function that is based on Frobenius norm. And so with this loss function is dependent only by current weights, so by client weights and by also global weights. Giving only these two elements, only these two sets of weights, is possible to design, to perform this loss function, and also in this case we can optimize the loss function, minimize the loss function in order to reconstruct the original data. So the main idea is to protect the weights and or the gradients when the clients transmit them. Different techniques was proposed during last years. One example, one of the techniques proposed is the differential privacy. The other is homomorphic encryption. So differential privacy is a mathematical framework that consists of introduced controlled noise into the data in order to protect the data owner privacy. So in order to protect the data, but without change the final output of our computation. In the case of federated learning, we are talking about training over local data. So if the client introduce some controlled noise on the local data set, it's possible to train the model without the original data, protecting the original data in the local client. So for the homomorphic encryption is a term that represents the class of encryption scheme in which it's possible to perform some computation over the encrypted data. It is based on property of homomorphic property. So homomorphic property of the group algebraic structure. So if we consider the plain text and the ciphertext do different sets, and if we consider these sets as part of a algebraic group, we can consider the homomorphism property over these groups, and in particular, we can consider the function, for example, the function E from P, from plain text set to ciphertext set, in which this equality is true. So as we can say, this equality is actual the encryption over ciphertext, because as we can say by the equality, if we perform this function E over encrypted data, we obtain a coherent result respect to plain text elements. So homomorphic encryption is very used in cloud computing scenarios in which we have a not trusted server. So if we compute some elaboration, some computation over stored data on cloud, homomorphic encryption is very famous in scientific literature. The homomorphic encryption schemes that are all the encryption algorithm with homomorphic property, they are grouped on 3 groups. So the partially homomorphic encryption, in which we are able to perform a limited operation over encrypted data over ciphertext set. Somewhat homomorphic encryption, in which we have a limited number of additional multiplication operations, and the fully homomorphic encryption that are the most innovative algorithm, in which we can compute an infinite number of addition or multiplication over ciphertext over ciphertext elements. So some of the most famous fully homomorphic encryption schemes are, for example, the Payer algorithm, that is an additive homomorphic encryption, is one of the first homomorphic encryption scheme, and it is a partial homomorphic encryption scheme because it's possible only to perform sum over encrypted data. Other important encryption scheme are BFV and BGV that are based on ring learning with errors problem. That is a very famous problem in post-quantum cryptography. One of the most innovative, one of the most new algorithm, homomorphic encryption algorithm, is CKKS, that is very innovative because it supports several operations over real numbers. So from a practical perspective, we can consider different libraries to implement homomorphic encryption. For example, Microsoft Seal, that is developed by Microsoft Research, or HE library, that is developed by IBM. Both of them implements fully homomorphic encryption schemes. The library that we use in our implementation on Flower is Tensile, that is a library for homomorphic encryption operation on tensors. It is built on Microsoft Seal. It's like a Python API built over Microsoft Seal, and it is designed for efficient processing of encrypted data in machine learning application, because it is designed for, as we said, for homomorphic encryption operation on tensors. So in our implementation, we have considered a client customization and a custom strategy implementation. So in these two components, in these two classes, we have introduced homomorphic encryption operation using, as we have said, a Tensile library. So we have re-implemented client and strategy classes, and so we use Tensile, as we said, because it's very convenient. In particular, it's very easy to integrate the tensor operation, the encrypted tensor operation with PyTorch library, with PyTorch tensors. So in our work, we distinguished three main phases in which we have realized homomorphic encryption operation. So we can consider in general in the flower flow, we can consider three main phases: the model initialization that is performed by the server that pick one random client, get the model, and spread the model among all the clients. We obviously have considered the client train phase, in which that is the actually training of the local model by each client, and the aggregation phase, in which we have also implemented the strategy, the aggregation strategy. In particular, we have implemented a encrypted version of federated averaging, and also fedprox, because the strategy is quite the same in fedprox and fedavg. The difference is in the training, in the client training. So the aggregation phase is logically the same. So we don't perform encrypt or decrypt operation in on aggregation side, because the aggregation, the average in this case is logically the same with respect to the nature of the data. Obviously, from a practical perspective, we have a difference. We have some differences, because we have to implement the aggregation exploiting tensile libraries. So this is like this is a sequence diagram of interaction between client and server during model initialization phase, and we can see that we encrypt the data of client, of chosen client, in order to spread them in an encryption in an encrypted way. Also, another important operation is the serialization of the parameters for transmission over the network from client and aggregation server. So during client train phase, we also have to decrypt and encrypt the parameters, because when each client get the global model, the global weights, we have to decrypt them in order to update them. So we have to decrypt them, set parameters in our local client model, update the parameters, and encrypt them in order to send them encrypted. So now let's give a look to some snippet of the code, just to understand what we have implemented. So this is the snippet of code to generate public key pair. Homomorphic encryption schemes are public key algorithm encryptions. So we have a public key, a private key, and we use public key to encrypt, and we use private key to decrypt. As we said, we override, we create a custom client, we customize the client object. In particular, we override fit method in order to insert this new approach, in order to insert the decryption and encryption of the parameters before and after the train method, the train function. So where we update the local parameters, because the update of local parameters is performed on plain text parameter. Okay, so for the aggregation, as we said, we also implement the aggregation, even if, as we said, logically is the same, because we don't decrypt or encrypt parameters on the aggregation server. So we also perform some evaluation, some tests, because we want to understand how much is the overhead introduced by the homomorphic encryption. As we can say, the overhead is quite relevant, and this is one of the problem of homomorphic encryption in any use case, in any scenarios, also in other scenario outside the federated learning context. And so, as we can say from the image, from the right image, I want to warn you that the y-axis is on a logarithmic scale. So the difference is quite relevant from FedAVG and FedAVG encrypted, or FedProx and FedProx encrypted. And so this is one of the problems. We have performed different tests in training and in aggregation. So in training, we have also compared FedAVG encrypted and FedProx encrypted, because the train is a little bit different, because in FedProx encrypted the function to minimize is a little bit different. And so as we said, this is one of the problem of homomorphic encryption is the overhead. So future works we have planned about this direction, about this topic. So we are publishing this work, and so we would like to extend this work with other homomorphic encryption libraries. For example, we know we met some Zama guys in Flower AI Summit, and so we want to interact with them in order to implement also with their library the same approach. We are planning to implement a Flower baseline with our work, and so we want to exploit this implementation in a practical use case. Another important point is related to the key management, because in this case we used regular homomorphic encryption scheme, but the optimal solution in security terms is to use a multi-key algorithm in order to have different keys, different private keys for different devices. And multi-key algorithm is a specific class of homomorphic encryption schemes that enable different private key, but a unique public key. And this is the optimal solution if we work with physical devices, because in this way we must not share the same private key with different devices. So that's it. Thank you for the attention. And so if you have some questions, I'm glad to answer them. Thank you.
Great, thank you so much for the presentation. Really, really interesting stuff. As you mentioned, we have worked in the past with Zama, and so they're really looking at how you can take FHE to production settings and really have it be applied. And so I was curious about what the main difference. I guess that would probably constitute the primary difference. I'd imagine those libraries are kind of built to be bulletproof, to be used today, and then this is more an exploration of how you would support these methods, I suppose. Is that what you'd say, or?
Yes. So with this new library, the new library, it's possible, but we should change some part of the implementation.
Oh, I see. So you're saying you could change some of the underlying pieces to their library potentially. Is that you're
yes,
kind of
because
yes,
because now we use the Tensile library, and so Tensile library owns specific methods to encrypt to perform arithmetic operation. So with a new library, we have to change some piece of code. It could be interesting to create a solution that is transparent respect to the library used, to the backend used for homomorphic encryption. This could be a very interesting work, but so it's not simple.
Yeah, sure. Great. Andreas has a question, so over to him.
Sorry?
Yeah, hi. Nice talk, very
Okay.
nice work, interesting work. I had a question about other algorithms, like if you, as you know, you did experiments on federated averaging. Have you also tried, is it possible to apply this to, say, Fed-Adam algorithms, where you have to do like some non-linear computation, like on the server side? Have you tried that?
So,
Like, would you run into, I guess my question
yes.
is, would you run into numerical instability issues? That's what I'm after.
Thank you for the question.
Mm.
Yes, it is possible. So with Fed-Adam, I think that the difference is that we use Adam optimizer to local update, right?
Yeah. So in the so no, the local update can be Adam in federated averaging as well. The difference is that this is Fed-opt ID, that you compute pseudo gradients. Like the difference on the server side is, instead of adding parameters, you need to take like the parameters minus the previous global model to get and sum that up to get the global, like a pseudo gradient. And then you like track momentum terms on the server side. So like you need to do some sort of it's like you need to compute some stuff, and that involves, I guess, products between tensors, power functions, and such things.
Yes, exactly.
I guess,
so I
do
think
you
that
need to tailor expand then, or to do that, this kind of, or what?
Yes, it's possible because we can perform multiply operation over encrypted tensor. So the problem is that in the plain text approach, we can use some libraries, like, I don't know, some optimizer, some built-in optimizer within very known libraries like PyTorch. So in this specific case, we should implement like from scratch the optimizer server side, because we have to implement. We have only arithmetic basic operation over tensors. So it's possible, but it's not.
But if you need to do like a square root, for example, of a tensor, and
yes,
then I guess
sure.
you need to tailor expand it, or how do you do it?
Yeah, sure. Yes, sure. It's not trivial to I think it's possible, but it's not
trivial. Thank you so much.
Thank you for the question.
Thank you.
Great, thanks for the question. Zed, you have a question, it seems.
Hey, it was a really good talk. I could not notice but think about, sorry, I could not stop but think about this idea of like, because I use in my project secure aggregation, which is basically, I guess what's the difference I would get if I were to use like something like this? Because I think in my case, I'm just doing aggregation on the server side. So what's the benefit I would get compared to secure aggregation if I were to use like fully homomorphic encryption?
So in your case, so if I think to your presentation, I think that maybe in your case you can avoid some leakage of the data, but I don't know. I think that you can avoid the operation of rendering that you perform client side. I think that you can avoid this kind of operation in your work because you can send the local trained weights also over the original personal images. Okay, so if I think to your presentation, I remember that you perform an operation client side in order to protect personal information, right?
Yes.
I think that with homomorphic encryption, you can avoid this your global GLP, if I remember well, the element, the operation.
Yeah, the global MLP. Yeah.
I think that you can avoid this kind of operation. I don't know if it's cheaper in terms of overhead, because as I said, homomorphic encryption introduced the relevant overhead. So I don't know if with your current solution you can save time. I don't know.
I think
it
one
could be
question
interesting to try.
I think if I have time, I have one follow-up question, which is basically doing like nerves, like training nerves on like homomorphic data is not like a solved problem also. So it could be something that could be interesting to see coming up, where you just say, I just send all the data, forget about decentralization aspect of it, but just send the data and doing nerf renderings on the cipher text. One fundamental issue though I have with this is that even though you can sort of create these nerf models, eventually these nerf models are representations of the data itself. So if the data, I guess it's still, you know, like if finally you're getting the data out with the nerf, like, you know, with the plain text version of the MLPs, then have you really secured anything? In my case, I'm not talking about this case, but I think in the problem that I had. Because eventually you basically are giving out data, like that's what you want to give, which you want to give some data, but not all data, right?
Yes, sure. Yes, I think that in your case, it's less, maybe it's less appropriate. But I think that could be also interesting because so you have to consider that the training is on plain text data. The local training is only for the aggregation that yes, for the aggregation that you have to implement the homomorphic encryption operation. So only over aggregation side. Okay, so the operation on client could be also performed on plain text data.
Yeah. So I think compared to secure aggregation, homomorphic encryption would not decrypt the average weights, right? So the server would never know the average weights also. It would just know the cipher text of the average text of average weight. So I think that's the benefit I think you get from secure aggregation to fully homomorphic encryption.
Sure. Yes, the aggregation is agnostic with respect to the encryption state of the data.
Thank you so much.
Thank you for the question.
Great. Well, we have run a bit over time, so I think I'll ignore some of the questions that are pending. But yeah, I think it's probably time we should wrap this up. So thank you, Alessio, for that talk. Great talk again.
Thank you. Thank you very much.
That was really awesome.